I'm going to talk for a moment about structure. We're all very familiar with the rectilinear form, and children just making a first picture of a house are very liable to use this cube. But the cube does not really have structural integrity. There's some diagonals in each of the faces of the cube here, and they are really responsible for its holding the shape that it is holding. I'm going to take away the, disconnect the, I'm going to take this away, and we find that our cube has no structural integrity whatsoever. So, but this is not lost its shape. This is what was giving the cube then its shape. It is our friend the tetrahedron. And a lot of people say, why do you use the word tetrahedron? Simply because it means a system that has 4 faces, tetrahedron. The Greeks then have one word where we need to say 4 faces, figure with 4 faces, so that they're more efficient than we are, so we might just well use a nice efficient word. Now, if we try to make a shape, something we might say about shapes. Here are some energy actions in the universe. There are enormous numbers of energy actions in the universe. One of the things I've learned is that 2 actions can't go through the same point at the same time. It's like knitting needles. It's very important to recognize that. And I found that the scientists I'm visiting here in England are now very excited by the realization that new axiom, that 2 lines of action can't go through the same point at the same time, is really beginning to prove very worthwhile. Because every architect and every engineer has assumed that if you can put a point on the paper and you run a great number of lines through that same point. In fact, all the geometries, Euclidean geometry, all the non-Euclidean geometries assume planes with points and lines going through the same points. But I've given myself a discipline which whatever I use in the way of tools must be experimentally derived. And when the mathematician says to me, I'm a very pure mathematician, and I have a line that hasn't any dimension, I ask him why he uses the word line. Because the word line is an experience. It's a word derived from experience. And I say, why, if you're so pure, can't you invent a new word that's so pure that means whatever you mean, that has something that has no dimension, no experience? He hasn't thought about that. But anyway, when we then become empirical, we say then that we find that 2 lines can't go through the same point. And on the cover of this month's Scientific American, you'll see a picture of the cloud chamber used by the nuclear physicists in bombarding the nucleus. And you read very recently about the discovery of omega minus. And what they do in the cloud chamber, bubble chamber, is to send in a very high-speed neutron or some other particle, and it suddenly collides with some other component, and then there is a parting of company, some angular resultants. And they're able to identify all the different nuclear components by the different kinds of angles that they take. Now, if 2 lines could go through the same point, same time, then there would be no such interferences, there would be no such panels. Each one would just go through the other one, there'd be no breaking up in angles. So when we get down to the bubble chamber, we're getting down the very finest lines nature's ever made. And it actually is not a continuous straight line, it's a series of little bubbles. And it demonstrates very clearly that 2 actions can't go through the point at the same time. So that's why we have interferences and why we have reflection and refraction. Anyway, let's get 2 actions that get very close to each other. They get what we call critical proximity, the way the Earth is attracted to the moon. So you get a mass attraction. So once these 2 are attracted to each other that way, then we find that they could they'd be like a pair of scissors. They hinge together. Now we have an angle that is really an unstable kind of an angle. And what I would like to do is to have a stable angle so that I'll be able to have a persistent shape. And that's what I mean by a structure. So I find that I take a hold of this side of the angle, the other side, these are levers. And the further I go away from that fulcrum, the less effort it takes to stabilize that angle. So having come to the very ends, we can take another action and let it cross here as a push-pull member. So with minimum effort, it stabilizes the opposite angle. So I find that triangle is a very extraordinary kind of device in that each side stabilizes the opposite angle with minimum effort. In other words, minimum effort is essential to the physicist because he finds that nature is always doing things with minimum effort. Now, we find then there are no other polygons that will do this. If I take out this, here's a square, we find it completely unstable, make more sides, this gets more and more, less and less stable. So that then the triangle is the only stable pattern. And now I'm going to want to do something which is, I'd like to develop then a local system that returns upon itself, that subdivides total universe into withinness and withoutness. And that is what I will then call a structural system. And in order to be able to have a withinness and withoutness, if I have two triangles hinged together like this, they simply come congruent. There's no inside and outside, too thin. So I find that the minimum subdivision of space is to have, say I have now two triangles. Again, it's like the hinge. I had a fulcrum before, now I have a hinge. So again, with minimum effort here, coming to the ends of the levers, I can stabilize that as opposite. So that becomes our friend, the tetrahedron. Unique then to the tetrahedron, to the system of omnitriangulated symmetrical systems is the fact that the minimum is with 3 triangles around each vertex. I can get 4 triangles around each vertex, and we call this the octahedron. You just count by counting off the faces, 8 equilateral triangles. So always 4. I can get 5 equilateral triangles around each vertex, and we call that the icosahedron. I can get 6 equilateral triangles around a common vertex, but they add up to 360 degrees. Therefore, it becomes a plane and goes to infinity and won't return upon itself. So it won't subdivide the universe locally into withinness and withoutness. So there are only 3 possible cases of omnitriangulated, omnisymmetrical, minimum effort shape stabilities. And that's tetrahedron, octahedron, and icosahedron.